Alright, thanks for watching and welcome to the vector space extravaganza. Today I would like to give you not only the definition of a vector space, but I also like to give you 25 examples. 25 examples? I know, but it'll be like those games where it says, oh, there's a game, 100 games in one game, and then you're like, oh, boy, it's not as exciting as you think. But I still think it's exciting because, and the reason I'm doing this is that vector spaces is such an abstract concept, and people are so overwhelmed with it. I want to show you that it actually occurs in real life. I basically want to give you so many examples that you're like, oh, well, those are interesting. Okay, so what is a vector space? Is some abstract set, so it could be anything you want, with two operations, plus and times, so addition and scalar multiplication, such that all those 10 properties hold. And I can look at this in case you haven't already. And those ones, they look so weird, but they're stuff you use all your life, right? You always use that u plus v is v plus u. Or you use that, foiling out. C plus d times u is cu plus du. So most of the properties are obvious. The ones that are not too obvious, and they're actually the most important ones, are those three things. Namely, a vector space is such that if you take two vectors and you still add them, it's still in the space, so it doesn't escape. And similarly, if you take a vector, u, and you scale it by c, then the resulting vector should still be in your vector space. And lastly, there's also a zero vector that does nothing. Namely, if you add u to 0, you still get u. Okay, but again, today is not much about the definition. It's really about examples. So let me start. Let me give you a bunch of examples. So the first example you've been dealing with for your life probably, it's Rn, or for example, R3. So technically, it should be infinitely many examples, but yeah, but for now, just maybe a basis of examples. Think of it this way. And why is it a vector space? Well, look, if you add two vectors in R3, you should get a vector in R3. And if you scalar multiply a vector, then you get 2 times that vector. And lastly, what is the zero vector? It's 0, 0, 0. So the first 3 properties hold, and you can check that all the other properties hold as well. But this is left as an exercise to the reader. Okay, so that was example 1, so 24 to go. Well, and as I said, more generally, Rn. But also, another example you've been dealing with are matrices. So take M2 by 2, which is 2 by 2 matrices. And indeed, those are also another example of a vector space. Because if you add two 2 by 2 matrices, well, you don't get a monster, you get another 2 by 2 matrix. 1 minus 1, 0, 1. And if you scalar multiply a 2 by 2 matrix, guess what? You get another 2 by 2 matrix. And what is the zero vector here? Interestingly, it's the zero matrix. Because if you add any matrix to the zero vector, you still get that matrix. So 2 by 2 matrices are vector spaces. And in general, n by n matrices. And it doesn't even have to be square. That's the nice thing. So third example, 2 by 3 matrices. So for example, 1, 2, 3, 4, 5, 6, plus 1, 0, 1, 0, minus 1, 0. You can add 2 matrices of the same size, and you get 2, 2, 4, 4, 4, 6. And you can also scalar multiply a matrix. 1, 0, 0, 0, 1, 0. And I just want to emphasize this number doesn't have to be an integer. You can scalar multiply it by square root of 2. And if you do that, you still get a 2 by 3 matrix. So So that's fine. And you can check the other properties hold. And the 0 vector, in this case, also is a 0 matrix. The matrix that does nothing. And so, also more generally, you can get m by n. So the space of matrices of size m by n. Okay, good. And so it's interesting. Here you will think of vectors. They can be actual vectors in Rn, but also matrices could be vectors. And even weirder, you could have polynomials being vectors. So the next space is just the set of polynomials of less than of some like of degree less than or equal to something. So example 4, let's call it P2, and it's a polynomial of degree less than or equal to 2. So polynomials with real coefficients of degree less than or equal to 2, and indeed you can add those, right? If you take x squared plus 2x and you add, I don't know, minus x squared, then you get 2x. And this is very interesting because you might be tempted to say, what about the set of polynomials of degree exactly 2? Well, technically that's not a vector space, because if you add those polynomials of degree exactly 2, you don't get a polynomial of degree exactly 2. Here the degree is 1, which is okay because it says less than or equal to 2. So that's fine. And also, you know, you can scalar multiply such a polynomial and you get 2x squared minus 4. So basically all the operations you've done before, but put in a more general context. And what is the 0 polynomial? We're literally the 0 function, the polynomial that's 0 everywhere. And of course we have P2, there's nothing special about 2. You could have Pn, the space of polynomials of degree less than or equal to n. And by the way, so sometimes this is called P2x because it's a polynomials with variables x. You could have it with any number of variables. So take example 5, P2xy, which is polynomials of degree less than or equal to 2 in 2 variables. Because indeed, if you, for example, add x squared plus xy plus x squared plus y squared plus xy, and you add it to x squared plus 2y plus 1, so it's a polynomial of degree less than or equal to 2 in 2 variables, you still get a polynomial of degree less than or equal to 2 in 2 variables, xy plus 2y plus 1. All right, and you may guess, well, we did it with polynomials, which are functions. Well, indeed, you could also have functions from R to R. Right. Again, just to show you, while you do linear algebra deals with vector spaces, it's such a rich theory because all the stuff we say in this course applies to all those spaces altogether. How amazing is that? So you're like killing 25 flies with one stone here in this case. So example 6, functions from R to R. For example, take f of x is e to the x and g of x is sine of x. Well, you can add 2 functions. What is f plus g? It's the function whose input is x, and whose output is the sum, so e to the x plus sine of x. Or you also have, 2 times f of x, which is just, in this case, 2e to the x. So the point is you can define f plus g, you can define a constant times f, and the 0 function is the 0 function. And there's nothing special from R to R. You can replace it with any variable, any interval. You can have continuous functions, differentiable functions, whatever. And in fact, not only only can you have functions from R to R, you can have functions from Rm to Rn. For example, one thing you dealt with multivariable calculus, you can have vector fields. In R3. For example, the vector field f of x, y, z may be e to the x minus z, y, x. So everything you've done in multivariable calculus, you can define with linear algebra. And more generally, as I said, functions from Rn to Rm. So maybe 2 inputs and 3 outputs. That also works. So as I said, really, really rich. And going back to calculus, we could also have discrete functions, which are sequences. So basically all of calculus is included in the study of linear algebra, which, okay, I'm simplifying a little bit because not everything is linear, but anyway. So we can have sequences. For example, if un is the sequence n, and Vn is a sequence minus 1 to the n, then what is u plus v? The sequence is just u plus Vn, it's just n plus minus 1 to the n. Let me write it this way. And then also 2 times the sequence un is just 2n, just the sequence 2n. So sequences, you can also write them, as vector spaces. And the 0 vector is the 0 sequence. And moving on, so you could have, well, vector spaces not only over the real numbers, you can have vector spaces over the complex numbers. So you can take the complex space, so Cn, for example, or C3 in this case. You can have the vector 1 plus I, 2i, 3. You can add it to 2 minus 1, 3i. And you get 3 plus I, and then minus 1 plus 2i, and 3 plus 3i. Okay. And the interesting thing is, well, the constants, depends what you're fixing first. You could have your constants just be your real numbers, and it becomes a vector space over the real numbers, or you could have vector space over the complex numbers, in which case your constants, C, well, as in C times this, C times I to 3i. This C, if your vector space is over the real numbers, C is real. If your vector space is over the complex numbers, then C is complex. But in both cases, it becomes a vector space. That's the cool thing. And also, so dealing with calculus again, so we did sequences, we did polynomials. Well, we could also have Taylor series, right? So power series, which are just infinite polynomials. Or formally, you can add them up, and you get a vector space. So 1 plus x plus 2x squared plus 3x cubed plus dot, dot, dot. Well, this is a vector in this vector space of power series. And we're not dealing with convergence issues, so we're not talking about convergent power series, but I think that might also be a vector space, the convergent ones. Because if you add 2 convergent power series, you get another convergent power series. Same with scalar multiplication. At least if it converges on the same interval and stuff, then it's okay. Okay, and then there's some fancier examples, and don't laugh at that. So, and I'm sure some people were like, sacre bleu, this is not a vector space, but in my case it is. Okay, so take the 0 vector, so nothing, water, and then syrup, and drink. Just want to show you it can be very abstract, but it could be a vector space. And in particular, how do you define your addition and your scalar multiplication? Well, water plus syrup. If you add water and syrup, you get drink. Or if you add syrup and drink, you get a very sweet drink. So yes, in fact, fact, syrup is the 0 vector, so this might be a very trivial vector space. But you could also, scalar multiply. So 2 times drink, well, it's still a drink. Or drink minus syrup, well, that's just water. So it's a very silly vector space, but I just want to show you abstractly you can have that. But here's a more interesting one. Example 12. Namely, just take the vector space 0, 1 times 0, 1. So if 1 is 0, 1 squared. Careful, this wouldn't be a vector space over the real numbers. It would be a vector space over some weird field, which is just the field 0, 1. And let me tell you how to add and scalar multiply vectors. Namely, it's 0, 1 with the convention that 1 plus 1 is 0. So then, if you add the vectors 0, 1 and 1, 0, you get 1, 1. But if you add 1, 1 and 1, 1, you would actually get the 0 vector. So in fact, minus 1, 1 is just 1, 1, just by definition. So you could have those fancier vector fields, and I think vector fields over, FP or something. And there are some really cool ones, because sometimes addition and scalar multiplication isn't what you think it is. So let's do example 13. So halfway done. Okay. Let's take the real numbers, but you define addition as follows. X plus y is x plus y minus 1. And multiplication, c times x, is cx plus 1 minus c. And what is really cool here, the number 1 becomes the new 0 vector. So 0 is just 1. Why? Because take x plus the 0 vector, that's x plus 1, and that's x plus 1 minus 1, and that's x. So you see, remember what the 0 vector does? It's a vector such that u plus 0 is 0 plus u, which is u. And that's precisely what we've done. If you add x to the number 1, you just get x. So it's kind of neat. So I think the number 1 is still the number 1 here, so that's fine. Because 1 times x, is just 1. Okay, so that was one example. And then I want to talk about sort of other examples, sort of in a more general context. So, turns out, to show something is a vector space, you don't have to really check all those 10 examples. Because there's some cases where you can recognize something as a subspace of a vector space. So a subspace, so just a definition, a subspace of V, so a subspace W of V, well, it's a subset of V such that the following three hold. So the 0 vector of V is in W. And just the three properties. If U and V are in W, then U plus V is in W. And if U is in W and C is a number, then CU is in W. So literally it's just the 0 vector is in it, it's closed under addition, and it's closed under scalar multiplication. In other words, if you have a set, and you know it's a subset of a vector space, you only have to check those three properties. Because turns out the other 7 are then for free. And this thing allows us to find more things. So this allows us to generate more examples. Because, for example, you have a line through the origin. And again, I'm not going to prove all those things because then the video would be 1 hour long, so that's not good. So example 14, a typical subspace is a line in R2 but the 0 vector has to be in it, so it's through the origin. Something like that. You have this line, goes through 0, 0. Well, the 0 vector is in it, and you can show that if you add 2 vectors on this line, you still stay on this line. And if you scalar multiply a vector on this line, you're still on this line. So indeed, it is a subspace of a known vector space, which is R2. That was example 14. Now example 15. Similarly, a line or a plane in R3. So plane or line in R3 through the origin. 0, 0, 0. Something like that. And you can also show it is a subspace of R3. So the point is, once you know the mother space, it's very easy to show something is a subspace. You just show those 3 properties. And in particular, there is a very important subspace that's sort of trivial. So it's an oxymoron, but the 0 space. So the space that just has the 0 vector for any vector space V, this is a subspace of V. So which gives us yet another example. But then there are fancier ones that you can generate using the subspace technique. For example, example 17, 2 by 2 matrices. So the mother vector space is a set of 2 by 2 matrices, but of the form AB 0D. So where this third entry is 0. And you can indeed check if you take 2 matrices of this form and you add them, you get a matrix of this form. For example, AB 0D plus A prime B prime 0 D prime. It is A plus A prime, B plus B prime, 0, D plus D prime. And indeed, this last entry is 0. So this gives us another example, which is a subspace in this example. And of course, similarly, you have all diagonal, or even upper triangular. So this matrix is upper triangular or lower triangular matrices. So it's also an important subspace of the matrices, of, I guess in this case, 2 by 2, n by n matrices. So you see, there's so many of them, and they're all so useful. See, that's why we're not wasting your time by teaching you about vector spaces, because all our theory applies to all those examples. Okay, another one, symmetric matrices. Matrices, where A transpose equals A. So, for example, 1, 2, 3, 2, 4, 5, and then 3, 5, 6. It's a matrix that's symmetric along the main diagonal. This thing, the set of those matrices also forms a subspace, hence a vector space. And going back to our functions, you can generate other kinds of vector spaces. So more specific polynomials. So, already at 20, okay. Example 20. Polynomials of degree less than or equal to n. So that's our mother space, but with the requirement that P of 0 is 0. So think, x squared, x squared plus 3x. You see, basically polynomials without constant terms. Those also form a subspace, hence a vector space. And one thing I alluded to is basically the set of continuous functions. This is a super important vector space in applications. So on an interval AB, so CAB. And you can generalize this, I think, all integrable functions in whichever sense you like. They're also a vector space because they're just a subspace of the set of all functions. And in particular, it is true if you add two continuous functions, you get a continuous function. And similarly, you can scalar multiply a continuous function and get a continuous function. And also, for example, the set of CAB, again, set of continuous functions with f of A equals to f of B. So basically functions whose initial value is equal to its final value. Also check that. If you add two functions with the same initial value, so whose initial value is this final value, then for f plus g, the initial value will be the final value. In particular, periodic functions of a fixed period, that also forms a vector space. Sometimes called continuous functions on the torus. So CT, so periodic function. It's interesting to find a basis for CT. Basically, that's how like Fourier analysis is generated, right? Because a basis would be just the exponential functions, you know, EI something. And of course, similarly, you can have it's like C1, which is once differentiable functions whose derivative is continuous. There's a very important space in geometry. Or C infinity, infinitely differentiable functions. Differential equations, that's so important. Or something called analytic functions. Again, functions which have power series. Also super important in complex analysis, for example. And we're almost done. So 23 examples, 2 more to go. So another one, it's simply, so there are some other very important spaces. So basically, if you have a matrix A, and you look at the set of solutions of AX equals 0, that is what's called a null space. So null of A is just the set of X where AX equals 0. And it turns out, and I've shown this in another video, null of A is always a subspace. So for example, if you take the set of solutions of x plus y equals 0 and 2x minus z equals 0, well, you can write this as null space of A, where A equals just the matrix, I think 1, 1, 0, 2, 0, minus 1. And by what I've shown, this is automatically a subspace and therefore a vector space. So this is also a vector space. Of course, you can write this as a line, but still, it's kind of cool, just abstractly. And not only does this work, so I guess this is one of my final examples, not only does this work for matrices, it also works for linear transformations. So in general, if you have a vector space and a linear transformation, the null space of T, or sometimes called the kernel of T, is just a set of X such that Tx equals 0. For example, take this very abstract transformation. T of y is y double prime minus 2y plus y. Then what this says is the set of solutions to this differential equation, so the solutions to y double prime minus 2y prime plus y equals to 0 is a vector space. Because it's precisely the kernel of this linear transformation. And this is why linear algebra and differential equations go so well together. Because you can always express solutions to what are called linear differential equations in terms of vector spaces. Which means, bam, you can apply all the concepts of linear algebra to differential equations. So that was one example, and I realize there's another one if you're interested. If you just take the set of all linear transformations, that's also a vector space. So you get a vector space, and you get a vector space. So just to show you they're everywhere. And that's why, linear algebra is such a rich subject, because we say everything about everything. So that's neat. All right, I hope you like this extravaganza. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.